Now let us see on how we can be able to analyze the actually inelastic corrosion that is in one dimension as well as the two dimension. So remember, we have two types of actually corrosion, and both corrosions obeys the law of the conservation of momentum. We have elastic corrosion, and thus where the objects upon collide they do not stick together, each object moves at its own speed. And we have elastic corrosion in one dimension as well as the two dimension, and of which we already discussed about that one. In case you missed that, just have to ensure that you have gone through that from whichever the source, or you can just have to check in my video playlist where you come across that one. And now we'd like to proceed further by looking at the inelastic corrosion that is in one dimension as well as the two dimension. But inelastic corrosion also obeys the conservation of momentum. So in inelastic corrosion, objects do stick together upon colliding. Either one object is moving, other one is at rest, or both objects are moving before they collide. But at the end of the day, after corrosion, the objects sticks together and they move with actually a common velocity, and there is no energy conservation in an elastic collision. And unlike with elastic collision, where energy is actually conserved. So in this case, you would like to look at inelastic collision, where actually objects sticks together after they collided. That is actually in one dimension as well as the two dimension. So now let's have it up. Let's say we have the object. Let's say this is the typical object. Now let me have them this way. Let's say this is the object of mass 1, and it is moving towards this direction with initial velocity given as u1. And let's say ahead of it there is the object. There is an object of mass 2 and also moving in the same direction with initial velocity given as, let's say, 2. It is also possible that it can move in the other way direction. It is okay, only that the velocity 2 can be negative, but just have to know that. And let's say after some point, let's say at this point, the object actually 1 collided with object 2. In this case, actually both the objects now are moving together. Let's say this is the case. Upon colliding, both objects actually are moving together. Now I should have it in this way. Let's say this is object 1, and let's say this is object 2, and after they collide, they are now moving together with the, let's say, a final velocity given as f. And of course, some scholars call it as actually a vc, meaning common velocity in that case. Now we have the object 1 moving to the light with the initial velocity given as u, and the object 2 with initial velocity given as u2. And upon the collide, the objects sticks together and they are moving together with the final velocity given as vf. So how should we have the law of conservation of momentum? In this case, this is a one-dimension collision where both objects are moving before they collide. So at the end of the day, Since the law of the conservation of momentum is being obeyed, it means we have m1 u1 plus we have m2 u2 and which is equal to, now since both objects will have the same actual velocity, which is said to be the final velocity, then we'll have m1 and plus m2 in that case, and it times the final velocity in that case. So keep that in mind. And this is for the objects both both moving before they collide, and that is in one dimension, as you can see. This would be the formula. And if it happens that the object 2, it is moving in the opposite direction, let's say instead of moving towards the light, it is moving towards the left. Let's say it is a head-on collision, but after they collide, they'll move towards that direction. It means we'll have the initial velocity u2 being given as the negative because it is moving towards the left. We'll have that as that. Now, what if one object is at rest? Let's say object 2 is at rest. It is no longer moving, it is stationary, but object 1 happens to hit it. Now, if this is the case, then it means we'll have now if one object is at rest, it means we only have the initial momentum before collision given as m1 u1, and is equal to m1 and plus should be m2 and times the final velocity. We'll have that actually upon colliding, where one object is initially at rest, and in that case happens that they collide inelastically. This would be the formula in that way. So that's how the actually inelastic collision can be expressed in basically in one dimension. So now how about in two dimension? Let's say we have the object of mass 1, let's say moving in this case with let's say initial velocity given as u1, and assuming that we have an object of mass 2 also moving in this direction, let's say with initial velocity given as u2, and after some actually at some point, the point in which the objects will have to intersect, assuming that they collide inelastically, where after collision the object happens to stick together and having, let's say, a final velocity given as, let's say, vf. Let's say this is the case where this is two objects sticking together. Let's say this is the case, and let's say this is object 1, and let's say this is the object, let's say object 2 in that case. Now if this is the case, how should we be able to analyze the aspect of the corrosion in this case? So we should have to depict the Cartesian plane, two-dimension Cartesian plane in this case. So this is regarded as the y-axis, and this is regarded as the x-axis, as you can see. So this is the x-axis, and still we can have it in this way. and also we can have it in this way. That's how you can be able to analyze that. So which means before collision, let's say object of mass m1, let's assume that it was moving in this direction at an angle of theta 1 against the vertical. And let's say object 2 is also moving at an angle of theta 2 before it collides with the other one. And assuming that after collision, both objects are moving at an angle of theta, actually at an angle of theta 3, actually after they collide or move, actually assuming that after they collide, both objects are moving at an angle of theta 3 with respect to the horizontal or positive x-axis. So now, how should we be able to go for the analysis of the collision and also aspect of the conservation of momentum? Now you can see that both objects are moving before they collide. At the end of the day, we actually would like to expect to have the momentum along x as well as the momentum along y, like the way we discussed about actually a two-dimensional elastic collision. It will be the same principle here. So we'll go for collision along x. Actually, we'll go for the collision momentum along x as well as the momentum along y separately. So let's start with the momentum for object 1. Initial momentum for object 1. So in this case, we're going to resolve into components. So what happens is that we'll resolve the initial momentum along x for object 1 actually separately. So which means we'll have, let's say in this case, we'll have that and also have that. So this is the initial momentum along x for object 1, and this is the initial momentum along y for object 1 upon resolving that. So principle remains the same, and where we'll have, by the way, should have that. So which means we'll have it as, now the initial momentum along x, it is going towards the positive direction. So which means we'll have it as m1 u1, and we'll have it as sine theta. Should be sine theta 1, because the angle is against the actually a vertical. In that case, it means using the trigonometric ratios, you see that we'll have the component x will have actually sine theta, that is in that case. And on the same note, let's also have to resolve the actually initial momentum for object 2. So this is what will happen. So go for that and also go for that. The initial momentum along x for object 2 is also positive because it is going towards the positive direction. So now which means we'll have it as plus m2 and we'll have it as u2 and times sine of angle theta 2, because the angle is against the variable, and which is equal to, now since objects are colliding inelastically, it means they'll have it means they are sticking together after they collide. So we'll have this one as that. So we'll have the object 1 plus object 2 and in that case times VF, so it should be this. Should be, now we'll have it as cos theta, should be cos theta 3, and that is times VF. So this will be the formula to be used, and for the actually for the conservation of momentum along x, we'll have this formula. And let's say this is equation 1. And basically you can be able to solve for whatever we have been told to, actually based on the given actually parameters. But this will be the analysis in terms of the formula. And on the same case, let's analyze the corrosion along actually y-axis, and this is for the actually x-axis. Let's go for the corrosion or the analysis along y-axis. So also have it in the same way. The initial actually momentum for the object 1 along actually y, it is the negative because it is pointing downwards. So in this case we'll have it as negative m1 u1 and cos theta 1. And for the object of mass 2, it is positive because it is pointing upwards. That will be given as plus m1 u1 and cos theta 2. Should be cos theta 2, and which is equal to, now we'll have the final that will be given as m1 plus m2 in the terms we'll have it as sine, it should be cos now, because the angles against the x-axis. They'll have, and also since on the same case, actually the x component of the velocity, actually the momentum, should be the y component of the momentum is pointing upwards. That's why it is positive. Then I'll have it as, should be a sine theta 3. In the terms VF. So this would be the formula along actually x-axis. Actually should be along y-axis, and that for the conservation of momentum. So keep that in mind. Let's say we have this another case, rather another system of the corrosion in a 2-dimension inelastically. Should be in an inelastic. Let's say we have the object m1 and it is moving horizontal in this case with the initial velocity given as u1. And let's say we have object 2, it is moving vertically up. Let's say this is the case, and it is moving with the initial velocity given as u2. Let's say given as that, let's go here. Let's say u2 like that, and after some time there reaches a point where they are intersecting. Let's say this is the point, and upon intersecting it happens that the objects are moving towards this direction, and they stick together. And let's say this is the final velocity. So how can we be able to analyze this case? Now we're going to have the Cartesian 2-dimension Cartesian plane. In that point to have, this is actually y-axis, and this is actually x-axis. Now in this case Let's say after collision, the objects are moving at an angle theta with respect to the x-axis. Let's say this is the angle theta. You also should have to understand that before collision, the object 1 is moving horizontal, the object 2 is moving vertical. So how should you be able to analyze the collision in this case? You should have to understand that the collision, actually initial momentum along x-axis, it is for actually only this object. And also initial momentum along y-axis, it will be only for this object, because the component of this velocity, actually the component for actually because the initial momentum along x for this object has no component, and likewise along y this one has no component, hence we'll have it as L. So now initial momentum for object 1 along x, we'll have it as just that one because it is moving horizontally already, and our wishes are equal to. Now in this case, after they collide, they are moving at an angle theta with respect to the actually horizontal. So we'll have to resolve into components. So this is the y component, and this is the x component in that way. So x component it is moving towards, it is pointing towards the positive direction, hence we'll have it as a positive. We'll have m1 and the plus should be m2, and the times we'll have it as cos theta times vf. That's how it will happen, because after they collide they are sticking together. And also in the same case, actually momentum along y will have it as m2 u2, and which is equal to m1 plus m2, and the terms will have it as a sine theta vf. So this will be the formula for the collision, actually for the momentum along y-axis. Then we can be able to find for whatever we are to have at the end of the day. So keep that in mind. So now, what if one object is at rest? Let's say we have this case. We have object 1 moving in this direction with our initial velocity given as u1. It happens that there is an object, let's say mass 2, ahead of it, which is at rest. Let's say it happens out that the object of mass 1 collided with object of mass 2, which is at rest. Let's say after they collide, both objects are moving together. In other words, they stick together. Let's say this is the case in that way, and they are moving with the final velocity given as vf. So what would be the way out for this case? So now principle remains the same. We'll have to develop the two-dimension Cartesian actually plane in that way, where this is the y-axis and this is the x-axis. And let's say we'll have it in this way, and also have it in this way, and also have it in this way. So which means, let's say before collision, object of mass 1, it is moving at an angle theta, let's say theta 1, with respect to the actual variable. And after they collide, let's say the objects are moving at an angle theta 2 with respect to the horizontal. So now, how can you be able to have the analysis of the momentum, and if that's the case? So now principle remains the same. we'll have to resolve this into components, where this is the x component and this is the y component. We also have to resolve this into components, where this is the x component and this is the y component. Now both x components will actually be positives, and also y components will also be positive because they are pointing towards the positive directions. So take note of that. The principle remains the same. For the initial momentum along x, we'll have it as m1 u1, and we'll have it as a sine, should be sine of angle theta 1. Mind you, the angles against the variable, and since the other object is at rest, it means we'll have it in this case. Then since they are colliding, actually since they are sticking together, we'll have m1 plus m2, that is plus m2, and the times we'll have it as cos theta 2, and the times final velocity in that way. So keep that in mind. And how about the momentum along y-axis? So also have it in the same way because it is the only one which is moving. So have m1 u1 times cos theta 1, that which is equal to, we'll have m1 plus m2 should be plus m2, and the times we'll have it as sine theta 2 and the times vf. So now this will be the formula along actually y-axis. So keep that in mind. Now how about if, let's say, both objects are moving in a 2 dimension, but after collision the objects are moving in 1 dimension? What would you say? Let's say we have the object of mass 1. Let's say it is moving in this case with the initial velocity given as u1, and let's say object 2, let's say it is moving this way with the initial velocity given as u2. Let's say this is the case, and let's say they actually collide inelastically. Let's say after they collide, assuming that they are moving horizontally, let's say they sticks together with a final velocity given as vf. So in this case the principle remains the same. We'll have to develop the actually xy coordinate system. Cartesian should be 2-dimension Cartesian actually plane, where this is the y-axis and this is the x-axis. And having it in this way, we have that, and also we have this. So now you see that, let's say before collision, object 1 it is moving at an angle of theta, let's say theta 2. Let's say object 2 is moving at an angle of theta, let's say theta 2. Record it as theta 1, by the way. It should be theta 1. And after they collide, the objects are moving horizontally. So what would be the analysis of the formulas? Actually, what would be the analysis of the momentum along x as well as the y? So you see that both objects are moving before they collide, so it means we'll have along x, we'll have it as m1 u1. Now since the angle is against actually x-axis, then we'll have it as cos theta 2. And you should know that the x actually will have the x component that will be pointing towards the positive, hence we'll have the positive. and a plus, and also in the same case, and for this one, the x component, it is pointing towards the positive. We also have it in the same way. M1 should be M2 U2 times, now since the angle is against the variable, it means we'll have it as a sine angle theta, should be angle theta 1, so should be that, and which is equal to, now since they are moving actually along x-axis, then it means we'll have it as M1 plus M2 plus M2 and the times VF. That's what will happen. Now how about the momentum along y-axis? So it means we'll have it as M1, so we just have to simply substitute. So for the momentum along y-axis, it means I'll have here sine theta in that case, so sine theta 2, so it should be a sine theta 2, that is, and for this case I'll have the cos theta 1. I understand you're following this. I'll have cos theta 1, because mind you, object 2, it is moving with respect to the actually angle theta 1, which is against the variable. So along actually y, we'll have the cos, and after they collide, since the objects are moving horizontally, it means we'll have the zero component of the final momentum along y, so which means we'll have it as 0. That will be equal to 0 because there's no final momentum along y. So those would be the formulas to understand, as you can see. Now let's say we have the object of mass 1, and before they collide, it is moving at angle theta 1, which is, let's say, 60 degrees with respect to the x. And let's say after they collide, it is moving at an angle theta 2, let's say, which is equal to 20 degrees with respect to y-axis. Let's say y-axis. And let's say object 2, and it is moving at an angle theta 3, which is equal to, let's say, 70 degrees with respect to the x. And before actually, then after actually collide, it is moving at an angle theta 2. It should be this. Now it should be this. Now the object of mass 1, it is moving at angle theta 1 at 60 degrees with respect to x. And for this case, object 2, it is also moving at an angle theta, should be theta 2. I should call it as a theta 2. Let's say theta 2, that is 70 degrees with respect to the x-axis. Now after they collide in elastical, they are moving at an angle theta 3. My pen is not properly doing the need of. Anyways, so let's say a theta 3. Let's say the angle is given as, let's say, 20 degrees with respect to the y-axis. So now, can you develop a system and to show what is really happening in the actual case. And how about if we have this? And it should also come up with equations of momentum along x as well as the y in that way. And how about if we have the object, let's say m1, moving at an angle of, let's say, 10 degrees with respect to x. The object 2 is moving at an angle of, let's say, 30 with respect to, let's say, y-axis. Should be y-axis. And let's say after they collide, and both objects are moving at an angle theta 2, let's say along x-axis, 20 degrees. Can you develop the system of, can you come up with a picture to show what is really happening, and also the equations which you have to understand? So that's how the inelastic corrosion can be well understood. So next you will have the typical examples on where I will be able to understand the concept and see if the corrosion is elastic or inelastic, 2-dimension or 1-dimension. Then we'll be able to solve some problems from there. So thank you, but don't forget to subscribe to my YouTube channel, and so that this kind of things should keep on being created. Thank you.